Density of a fluid is the measurement of how much mass a fluid has per unit volume or per unit area if we're talking about a section, a very thin section where the area is actually the volume. But in general, we're talking about volumes. For heavier fluids such as mercury, which is a metal fluid, a metal liquid, the mass is high, so it exhibits a higher density, the mass per unit volume. As for gases, the molecules are very much lighter and they are much scattered from each other, so the density is much lower. That's why gases are much light. So gases also are characterized by a changing density with temperature and pressure, which is not very fond of water and other liquids. Hot gases collide against each other more frequently when there's a high temperature, exhibiting a higher pressure than cold gases, but at the same time they expand, becoming lighter with a lower density, lower mass per unit volume. Density is given by the following formula, where ρ is density, m is mass, and v is volume. Ρ in kilograms per meter cube is equal to mass in kilogram divided by volume in meter cube. So for examples, water, pure water, 4 degrees is 1000 kilograms per meter cube. As for mercury, and notice how heavy it is 13 tons, 0.6 for 1 meter cube. So it is much heavier than water. So again, as a review, ρ equal m over v. Specific gravity. Specific gravity is the ratio of a substance density to water. So it's a ratio of comparison between a fluid and water. This is what we call specific gravity. It is dimensionless, used only for comparison between different fluids. So Sg is equal to the ρ of the fluid divided by ρ of water. Fluid density divided by water density. Another property is the viscosity. Usually when we say viscosity, we are referring to the dynamic viscosity. So viscosity mu is expressed in poise. 1p is equal to 0.1 Pascal, which is the unit of pressure, by the way, is a measure of the fluid's internal resistance against flow, also called internal friction between between the molecules of the fluid itself. It describes how thick and sticky a fluid is. As an example, honey is very viscous, so it flows much slower. Its molecules have, a very high internal resistance and intense resistance force among each other. So it drops very slowly from a spoon. Not only that, but it forms a thread. The molecules remain stuck with each other. All right. So it is very highly interconnected and has a high internal pressure, which is about 10 Pascal per second. Water, on the opposite side, flows much easier, has hence a very lower viscosity, which is 0.001 Pascal per second, flows much easier. Pa again stands for Pascal or Newton per meter, which is the pressure unit. Shear stress. Shear stress in solids is the force applied parallel to a surface of a solid while the bottom is fixed. It causes a displacement delta L, as you see in this picture. Shear stress tau, expressed in Newton per meter square divided by meter square, which is times m to the power minus 2, is equal to the force in Newton divided by area in meter square, which is the area of the upper surface of the solid. In fluids, however, shear stress causes upper layers to slide against each other, or to slide against lower layers. It is, how easily the upper layers flow is subject to the fluid's dynamic viscosity, as we see in this formula. Shear stress is proportional to shear strain rate, which is how fast one layer of fluid slides relative to its lower layers. Tau is equal mu times du over dt, where tau is the shear stress in Pascal, mu is the dynamic viscosity in Pascal per second, and du over dy is the velocity gradient or rate of shear strain parallel to the flow direction, parallel to the direction of the flow. Kinematic viscosity, which is a counterpart, if you will, of dynamic viscosity, expressed in Stokes, we will talk about that, defined by nu. It is the measure of the fluid's resistance to flow when it is under the pull of gravity or another body forces, such as a solid plane. An example for that is oil flowing against a glass panel, where the forces that keep a part of the oil stuck on the surface are evident. Kinematic viscosity is expressed below in this formula. In Stokes, 1 Stoke is 10 to the power minus 4 meters square per second. Mu expressed in Newton per, times S divided by meter square. Rho in kilograms per meter cube. So kinematic viscosity nu is equal to mu over rho. It is a definition of the tendency of a fluid to resist a flow. All right, it's a measurement of fluid's resistance against a flow. So for water, as an example, it is 1 centimeter Stoke. For air, 15 centimeter Stokes. And for olive oil, it is 80 centimeter Stokes. Surface tension. Fluid molecules pull each other with an equal cohesive force in all directions that keeps them intact together. That's why they don't fly apart. The molecules on the surface are pulled inwardly down by lower layer molecules with no upward forces to balance it, since they are not surrounded with other molecules on top. This creates a thicker layer of the fluid, making it harder to break or dissociate from external forces. So the surface tension, gamma, expressed in Newton per meter, is defined by force F divided by unit of length. So gamma is equal to F over L, or F divided by L. Fluid temperature. In scientific terms, fluid temperature is the average kinetic energy of its molecules. All right, so it's the equivalence of its kinetic or the kinetic energy of molecules. So let's talk about temperature in thermos and fluid dynamics is a critical factor that affects other properties such as density, pressure, velocity, viscosity, and heat transfer. So it is a very deterministic factor in fluid dynamics. Other parameters related to temperature are listed below. You have thermal energy, which is Q, or measure of the average molecular kinetic energy. Heat capacity, or amount of heat needed to change a fluid's temperature. Specific heat, smaller c or lower case c, is the heat capacity per unit mass. Enthalpy, or the total heat content of a fluid per mass unit. And internal energy, U, or total energy in a fluid due to a molecular motion. Heat transfer and fluid temperature. Heat transfer in a fluid is the measure of the amount of heat energy, which is Q, expressed in joules, needed to change its temperature from one value to another, T initial to T final. Q is mc delta T, where Q is the heat energy expressed in joules, M is the mass of the fluid in kilograms times C. C is the specific heat capacity. So it is specific for and different for each type of fluid, expressed in joule per kilogram per Kelvin. 1 Kelvin is equal to 1 Celsius plus 273. And delta T is the change of temperature, which is T final minus T initial. Convection and heat transfer, or convective heat transfer. Convective heat transfer is when a fluid transfers heat to and from a solid by the means of superficial contact, This is how refrigerators work, by the way. It is the result of both fluid movement against the solid surface and conduction, thermal conduction. Q is equal to HA delta T, where Q is the heat transfer in watts, H is the convective heat transfer coefficient in watt per meter square per Kelvin, A is the surface or the area of contact, through which the heat is being transferred from the fluid to the solid. And finally, delta T is the change in temperature, which is T final minus T initial. Let's talk about types of fluids. You have ideal versus real fluid. An ideal fluid is theoretical, meaning that it doesn't really exist and has specific properties that are used to simulate or to understand the fluid behavior under certain conditions, assuming it was idealistic. So what are these characteristics? First, it is incompressible, meaning that the density is constant. It doesn't change regardless of the pressure value or temperature changes. Of course, they cannot be intense, otherwise this density will change. Second, no viscosity. It doesn't resist shear stress and the internal friction is minimal, not the case for liquids. Irrotational flow, the fluid has no vortices, so you have a laminar flow. It flows with straight lines, actually curved lines, but you don't have eddies or swirls or vortices like wake turbulence at the tail of an airplane. Vortices are caused by turbulence in the flow, as you know. No heat conduction, so it doesn't transfer out or receives a temperature exchange from the outside, from an external factor or an external body. No conducting and non-reactive. No conducting meaning it doesn't conduct electricity and it doesn't transform or react due to chemical processes. It doesn't change because of chemical reactions. And finally, flows steadily, so the flow is often assumed to be steady.